Melting, freezing, and sublimation, 12.5. So we talked about the transition between liquids and gases, and vice versa. Now we're going to talk about solids. So if we think about a solid, as the temperature of the solid increases, the vibration of the particles becomes greater. Thermal energy related to kinetic energy. At the melting point of that solid, the atoms or molecules have enough energy to overcome the intermolecular forces that are holding them fixed in their position, and they're allowed to move relative to each other, and the solid becomes a liquid. So here we have an illustration. This is the ice, and molecules of water are held in a particular arrangement here. And as the temperature goes up, and when it gets to 0 degrees Celsius, these particles have enough vibrational energy, thermal energy, that they can break loose and move freely relative to each other. They're not escaping yet. They're still kind of held together, but they can move around. So it's like you've been released from your seats. You can mill about the classroom, but the teacher's not letting you leave the room yet. As long as the water and ice are both present, the temperature will be 0 degrees Celsius. And this is similar to what we saw with boiling water, where the temperature remains constant until the state change is finished. So when we have a mixture of water and ice, it's always going to have a temperature of 0 degrees Celsius at 1 atmosphere of pressure. The pressure will affect that temperature somewhat. The temperature will not rise until all of the ice has melted. And so this is another idea that's just not really obvious. But, here I have my drink, and there's ice and water in there. And where there's ice and water, it's 0 degrees Celsius. Well, that might be a little bit off because it's not pure water, but you get the idea. So if we look at a heating curve for melting, similar to what we looked at for boiling, here, if we take water at minus 20 degrees, it's frozen into ice. And as we add heat, the temperature of the ice increases until it gets to the melting point. At the melting point, now these particles, these molecules, begin to slide next to each other. They melt. And all of the energy that's being added goes into freeing the solid molecules into liquid, and it does not increase the temperature. Once all of it has melted, then the temperature will rise. And when we get up to 100 degrees Celsius, then we'll see another plateau where the temperature stops at 100 until everything has boiled away. So there's energy involved in melting and freezing. When we add ice to a drink, it cools the drink because melting is an endothermic process, just like evaporation is. So the ice melting absorbs heat from the liquid and cools the liquid. The energy is needed, is coming into the solid to help those particles break free from some of their intermolecular attractions. The opposite is true, that freezing is exothermic. So when a liquid freezes into a solid, heat is released. Okay, this is not obvious. But what is your refrigerator freezer unit doing? It is pumping heat energy out of the inside, and that energy, that heat has to go somewhere. It generally goes to the outside of the refrigerator freezer in the back, and then oftentimes there's a fan that blows it out. And you may have noticed there's always a slightly warm breeze coming out the bottom of your refrigerator. It's a great place to dry shoes, by the way. My kids, they get their shoes wet. You spin them in the washer, get all the excess water out, lay them on the sides in front of the refrigerator, and they're dry by morning. So there's I guess they call those life hacks now. There's a life hack for you. I have kids your age. I hear these things. So freezing is exothermic. So how does your freezer turn the water in the ice cube trays into ice? Well, it's pulling heat energy out. because when water freezes, it gives off energy. And so we need to remove that energy, and that will cause the water to freeze. That causes the temperature to be lowered. And this is, we talked about this on Wednesday, this is why we water the citrus trees when it's going to freeze. Because all that standing water, as it freezes, it releases energy, and the temperature will not fall until it's all frozen. And so that helps to moderate the temperature. So just like there was a heat of vaporization, we also have heat of fusion. So this is delta H again, but FUS for the subscript here for fusion. Now evaporation or vaporization made more sense to us. Fusion, what's that? Fusion is melting. So think of it this way. What happens if you put a bunch of chocolate chips in a saucepan and put it on the stove and turn the burner on? They melt. And as they melt, they fuse together, right? So fusion is melting. So heat of fusion is the heat required to melt 1 mole of a solid. So here we have solid water going to liquid water, and the heat of fusion for this is 6.02 kilojoules. This is positive because in order to melt something, you have to put energy in. Now, if you printed the slides out before yesterday, these were backwards. This one and the next one were switched around, so sorry about that. But delta H is positive. The opposite process is freezing, going from a liquid to a solid. And here, delta H is negative because the energy is being released. So we can do calculations with this too. We can use the heat of fusion to calculate the amount of heat energy needed to melt a given amount of a solid. And we can use that heat of fusion as a conversion factor between moles of solid and amount of heat needed to melt them or released when it freezes. So let's calculate the amount of heat absorbed when a 15.5 gram ice cube melts at 0 degrees Celsius. So I can't remember the number, 6.02. Okay, thank you. So let's just write that up here so we don't forget. So delta H of fusion is 6.02 kilojoules per mole. Fusion is melting. Melting is endothermic. That's a positive number. And this is a decimal point. It's just a really ugly one. So again, we have this kilojoules per mole thing. We're calculating amount of heat, and based on our experience with the previous problems, we probably recognize that the kilojoules is probably going to be good. To get to kilojoules, we need to know the number of moles, and they're giving us the mass in grams. So we're going to have to take the mass and convert to number of moles, and then we can apply the conversion factor. So this ends up being very similar to the first problem we did. 15.5 grams of water, because ice is water, it's just solid. Times, we're going to convert to moles, times, and convert to kilojoules. We want to cancel the grams, so those units come down here. We want to cancel moles, so moles comes down here. Dimensional analysis is just crazy useful. I've had a couple of students, and one of them in particular in a different class, he kind of fought me on this, and then we started doing conversions that he wasn't familiar with the units, and so he realized he had to figure it out, and he figured it out, and he came to me, he's like, that's the best thing ever. He was so excited about it because it finally made sense to him. So if it hasn't made sense to you yet, okay, it's not too late. The dimensional analysis, I told you at the beginning, we're going to use it a lot. You put the units in, and so you don't have to worry, am I supposed to multiply, am I supposed to divide? The units tell you what to do. So we've already figured out that the molar mass of water is 18.02. 1 mole of water weighs 18.02 grams. Kilojoules per mole This is heat of fusion at 0 degrees, 6.02. And the fact that that's 6.02 and Avogadro's number is 6.022 times 10 to the 23rd, pure coincidence. Okay. Some of the other things that line up like that are not coincidence. That one's just pure coincidence. 15.5 divided by 18.02 times 6.02 equals. We should have three significant figures, so we'll say this equals 5.18 kilojoules of energy. Any questions?
So the fusion, that's a number that'll be given to us, or again, we'll have to look at it in the chart?
Yeah,
Okay.
the heat of fusion is one of those constants that you either are given or you look it up. You don't memorize stuff like that. It's a waste of brain cells. Save those for important things like Avogadro's number. Any other questions? So here's a diagram showing a heating curve for water, beginning with ice at minus 25 and ending with steam at 125. So let's just talk about this real quick and make sure we understand what's going on here. So over here in this section, what's happening? This is ice. It's below 0 degrees Celsius. What's happening to the ice? Is it melting here? No. It's warming up. Okay? So ice can be at like minus 1 degree Celsius, or it could be minus 75 degrees Celsius. Okay? Just like metal, which is a solid, can be at different temperatures. So in this first line, we have ice warming up. What states of water do we have present in this section? What's happening there? The ice is melting, right? So here we have ice and water, or solid and liquid. So in that flat spot, we have solid and liquid. And then this next section, what is the state of H2O here? It's a liquid, because that represents the liquid warming up. So this is liquid, water. Then we get to this section up here, what's happening? The water's vaporizing or boiling. So what states of water are present? Liquid and gas. Yeah, I zoomed in too far. So here we have liquid and gas. And the words we use are water and steam. And then once we get to this point where all of the water has been converted to steam, what do we have present here? The gas, just the steam. And this is not just true for water, this is true for most substances. There are some substances that do some kind of funny things. And there are some substances that when you heat them, they don't actually melt, they fall apart. They decompose. Okay, like sugar. If you heat sugar, it doesn't actually melt, it caramelizes. It undergoes a chemical reaction. But many substances will do this. You take the solid, you add heat, it warms up until it reaches its melting point, at which point the temperature remains constant until it's completely melted. Then you can heat up the liquid until it begins to vaporize or boil. And then you have the liquid and the gas both present until all of the liquid has been turned to gas, and then the gas will heat up. Any questions about heating curves? You can think of them as a heating curve going this way. You can also talk about them as a freezing curve going backwards. So as we remove energy, we would travel the other way along the line. So melting and freezing, we understand. Sublimation is kind of a weird state change. Sublimation is going directly from the liquid state, directly from the solid state. I'm looking at the word solid and saying liquid. It's a physical change directly from the solid state to the gas state. So not melting, but just going directly to a gas. Not all substances do this. In fact, I'd probably say most of them do not do this to any appreciable degree. But one of them that we're familiar with is carbon dioxide. And the solid form of carbon dioxide we call dry ice. Dry ice does not melt at atmospheric pressure. You have to increase the pressure significantly to get it to melt. But at normal atmospheric pressure, it doesn't melt. It goes directly from the solid to the gas. And that's why it's called dry ice. What happens if you pack a cooler with regular ice? As the day goes on, the ice melts and your sandwiches get all wet, right? So you have to be careful about that. If you pack a cooler with dry ice, as the day goes on, the dry ice gradually disappears, but there's no liquid in there. Your cooler stays dry. It's ice that stays dry, hence the name dry ice. Okay, it's subliming. It's going directly from the solid to the gas. And it starts doing this at minus 78 degrees Celsius. So at minus 78, the molecules have enough energy to leave the surface of the dry ice and go directly into the gas state. Here's an illustration, actually a photograph. So here's a chunk of dry ice sitting on an iron ring. And you can see what looks kind of like smoke or a vapor here. Okay, what you're seeing is not the carbon dioxide, because carbon dioxide is colorless. There's a lot of carbon dioxide in the air in this room, but we can't see it. Well, what I believe we're seeing here is the carbon dioxide is subliming, but the gas that's coming off of it is cold enough that it causes the water vapor to condense. And so we're seeing actually the water condensing because of that cold gas that's coming off of this solid. It's a little bit like when you go outside in the winter and it's cold and you breathe out and there's this cloud. It's like, but I wasn't smoking. Where's this smoke come from? Well, it's the warm air from your lungs that has lots of moisture in it, lots of water in it, and it comes out and it hits that cool air and it condenses. And that's what fog is little droplets of water condensed in the air. Well, dry ice is pretty cool. Just need to be careful not to put it in a sealed container, because that's called a dry ice bomb, and several people in California have recently gotten in big trouble for that at the airport, right? Dry ice bombs, not a good idea. Don't mess around with that. Regular ice also sublimes, but much more slowly. But it will sublime at temperatures below 0 degrees Celsius. Now, we don't get snow around here. I remember the last time we got snow. It was January 25th, 1997. No, 98. It was 98. Because James was in kindergarten, and I thought it would be fun for him to stay home from school, but he insisted on going to school. And it was my parents' anniversary. So that's when it last snowed in Reedley. Where I grew up in Minnesota and Iowa, it snows a lot. So you get snow, and even if the temperature stays below 0, the snow will gradually disappear because it's subliming. It's going from the solid state to the gas state. This happens in your freezer. It's happening in your freezer at home right now. Have you ever found forgotten ice cubes in the back of the freezer? Has that ever happened to you? And they're smaller than the rest of the ice cubes. We're like, how did we get these miniature ice cubes? They're like half the size. What happened to them? Well, they sublimed. They're sitting back there for way too long, And they're gradually going from the solid state to the gas state. The gas is free to move around, and it goes and makes ice crystals on the sides of your freezer and stuff and frosts up your freezer. So this also happens in the food in your freezer. And this is what gives rise to freezer burn. The freezer, food that's been frozen for a long time gets dried out and nasty, right? So say you have a bag of tater tots and you left them in there for a while. And then you open them up, and here's the tater tots, and they look kind of dry, and then there's all these ice crystals in the bottom. You think, why would the manufacturer put all this ice in the bag? It's a good thing I pulled it out frozen, or they'd be soaking wet, right? Where did all the ice come from? There's moisture in the tater tots. There's water in the tater tots, and it sublimes into the gas state. It can't get away because it's in a bag, so it goes somewhere else in the bag and ends up condensing there. So here's a couple more life hacks. So how can you avoid that? Well, you can use a deep freeze, which has a temperature that's significantly colder than 0 degrees Celsius, because the colder the freezer is, the less sublimation there is, and the less your food will get freezer burn and get dried out like that. The other thing you can do is to use like one of those food saver bags that sucks all the air out. And you can even do that on the cheap with like a Ziploc bag and just squeeze all the air out of it. Or wrap the meat in foil and then put it in a bag and squeeze all the air out. You want to minimize the amount of air that's around the food, because when the ice sublimes, it goes into the gas state. If there's nowhere for it to go, it's going to come right back, and your food's going to be better. So, it's an interesting application to actual life.